So we can kind of define or simplify the neural relationship between stimulus X goes into some black box and we get some sort of output Y, which is the response. And so the hard question is like, what's in the black box, right? So one of the model is called a Linear-NonLinear-Poisson model, which, and in short we call it LNP model. So once the input, some stimulus goes inside, we have the linear filter, which we'll call K. So, you know, the output here will be K times X because it's the linear filter. So that's what we have here. And then it goes into the Kx goes into the point nonlinearity. This is basically a nonlinear function, and so I guess we could say the Kx is also the X this comma. So X comma will fall somewhere along here, and we have this corresponding Fx comma, right? And that's what it is over here. And this output is the gamma t. And this gamma t goes over here into Poisson spiking. Poisson's is about it's like as the dice implies, there are independent events that are there's a probability of some independent events occurring. So independent to each other, and then they comes out to the output. So there's that. So if we visualize this LNP, the Linear-NonLinear-Poisson model in time, so we have some stimulus, and then we get a resulting response, some sort of spike, right? And which we can represent as 0 or 1. If it fires, it's 1. If it doesn't, it's like 0. And there's got to be some sort of relations between the stimulus and response, right? So we have this K, which is the linear filter, and we have this F, the point nonlinearity. So how do we determine the K and F? So how we get this? So we're gonna determine this some arbitrary time step called dt, or the range of time, and we were gonna combine it into some. It could be average of the spike, or I mean the stimulus, or something like that, and then we put that into the linear filter, and it's going to give us some kx, the average value times the k. And once you have that, we're going to put it into the point nonlinearity. The value will correspond to some value over here, and then it's going to give you some value output of it. So so we have to know the function for the nonlinearity as well. And what this maximum likelihood methods are doing, so we have some parameters for these two. So like, what parameters should we use to maximize the likelihood of this observation, right? So Bayes' theorem, simple thing. So the PAB is a probability of, or given B, what is the probability of A, right? And this is the probability of. So we define it as the probability of Y given X is called the likelihood, where the X and Y are both stimulus, and the response of probability of response given the stimulus is the likelihood. Makes sense. And the other way, the probability of stimulus given the response, we can think of it like the reversely, is called the posterior distribution. And then Px and Py are each respectively called the prior probability of the stimulus and the response distribution. So going back to how do we maximize the likelihood of the observation with our model parameters? So parameters, we're going to narrow it down to a theta over here. And we have this X input and this output. So what's the probability output given the input and parameter. And the maximum likelihood model is over here. So the parameter theta, so probability of output or the response given the stimulus and the parameter, like give me the theta, they give me the maximum probability, is what this is saying. So joint density. Probability of observing the sequence of spikes given the development process in homogeneous Poisson process with known rate function. Honestly, I kind of don't understand this. So if you go through this complex math, we get this spike triggered average minus proportional to k, stimulus distribution is spherical symmetric. Blah, 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 blah. So they compared it with the spike triggered average and covariance with the estimate. And it seems that actually STC spike trigger covariance does pretty well. Yeah. And nowadays LNP are kind of outdated, and they're using GLM, which is a generalized linear models. Because we said Poissons, but Poissons are unrelated to each other, independent events. But we know that like the spiking of neurons are intertwined with each other. There's some like right after the spiking, we have this like reflection period where the spiking does not occur. So what we do is we have the generalized linear model here. We have the post-spike waveform going back to is over here, in between the linear field and nonlinearity, to take account for that. So we take account for the dependency. And if we actually, so this is like all simulations, but if we see over here, there's some stimulus, and if you see the actual like data, and we have the, actually I think this is from like some animal neurons or something, and we have this LNP model and then the integrated fire models, and these are just zoomed into over here. We see that they're pretty similar. We have this like some wave-like things going on, and integrated and fire actually demonstrated pretty well, whereas LNP doesn't do so over here too. But both are okay, seems okay. And then rate and variances, it seems that the actual data, the ground truth and the integrated fire seems to be most similar, whereas LNP is slightly off, but still not, shows it's generally the same trend-ish.